All right, so far we've talked about, in 10.1 we talked about parametric equations, and then in 10.2 and 10.3 we talked about polar equations. In 10.4 and 10.5 we'll talk about conic sections, and then in 10.6 we'll talk about conic sections in polar form. So it'll all kind of come full circle, I suppose, in some ways. Anyway, this lecture, 10.4, should just be review. So I have a whole bunch of links in these notes, and by the way, I'm going to put these notes on Canvas with this lecture, so you're welcome to print these off or whatever. But I'm not going to show you the links here because, you know, I'm assuming that most of you have already seen these constructions before. So I'm just including the links so that you can take a look at them if this is, you know, brand new to you, or if you just need a lot of kind of refresher on this material. Okay, but otherwise I'm going to assume that you have the picture in your mind already of what it is that we're talking about. Okay, so just as a reminder, conic sections, geometrically speaking, a conic section is the intersection of a plane and a pair of hollow cones. The intersections of these three-dimensional objects are really two-dimensional cross-sections, so they can be described as a set of points in a plane. And so there are three types of conic sections: parabolas, ellipses, and hyperbolas. Circles are just special kinds of ellipses, and that's what you get when you take a couple of cones and put them tip to tip and then slice them with a plane. You either get a parabola, an ellipse, or a hyperbola. And again, you can watch this animation to kind of convince you. But what we're going to do is we're going to give the two-dimensional cross-sectional description of these things as, you know, points in a plane. So here's how this works with a parabola. And again, I'm assuming that you've probably seen this already. Okay, but a parabola is the set of all points in a plane that are equally distant from a fixed line and a fixed point not on the line. The line is called the directrix, the point is called the focus. The turning point of the parabola is called its vertex, and the line that passes through the focus and vertex is called the axis of symmetry. So here's an animation that actually shows you, like, physically how you get a parabola by taking the points that are equally distant from a fixed line and a fixed point. Now, it's traditionally, when we're dealing with parabolas, we like to denote the distance between the focus and the vertex by p. So the distance between the focus and directrix would be 2 times p. And using that convention, we can describe the equation for a parabola as follows. So if p is a positive number, the equation of a parabola with focus 0p and directrix y equals negative p is x squared equals 4py. Now, there are other kinds of parabolas, right? You could have a parabola with focus 0p and directrix or rather 0 negative p and directrix y equals positive p. Or you could have a parabola with focus p0 and directrix x equals negative p. Or you know, and then there's negative p0 and x equals positive p. And that all, you know, will affect the way that the parabola opens and everything like that. This particular parabola with a directrix of negative p and a focus at 0p is going to open up, right? So the picture we get is, you know, you've got, you know, maybe your coordinate axis, your directrix is at negative p, and then your focus is at 0p, and the resulting parabola would have to look something like that. Okay? All right. So this is the parabola that we're talking about in this theorem, but the other three cases are similar. And I'm just going to prove this quickly. Okay? So let's say that xy is a point on the parabola, and let's draw a picture of the parabola with focus, directrix, and our point xy. Oh, I guess I didn't need to draw it over here on the margin because I was going to draw it anyway over here. Okay, so this is the situation. So this is our directrix, y equals negative p, and this is our focus, right, 0p, and the resulting parabola would have to look something like this. Okay. So if we take a random point on this parabola, like this one right here, this is going to be our point x, y. And what did I say to label? X, y is a point on the parabola. Let's draw a picture of the parabola with focus, directrix, and our point x, y. Good. Now, by definition, the distance from x, y to the focus is the same as the distance from x, y to the directrix. Okay, that's just by definition, right? That's what a parabola is. Sorry, up here, right? It's the set of points equally distanced from a directrix and a focus. So, and I may not have drawn this very well, but that means that this segment and this segment, right, have to be equal length. By the way, this would have to be the point x negative p. Okay, so the distance from xy to 0p, to our focus 0p, well, that would just be distance formula, right? It would be the square root of x minus 0 squared plus y minus p squared. Okay? The distance from xy to the directrix is the length of the line segment that goes from xy and intersects the directrix at a right angle. So the point where they intersect would have to be x negative p, just like we said. And so the distance from xy to the directrix would have to be the square root of x minus x squared plus y minus negative p. So y minus negative p squared. So there's that distance. Since these distances must be the same, we have the following, right? So x minus 0 squared would just be x squared. So we would have square root of x squared plus y minus p squared has to equal the square root of, well, x minus x minus x squared would be 0 squared, so that's just 0. And then y minus negative p is y plus p. So this is y plus p squared. Okay. You can square both sides to clear the radicals, right? And then you've got this, and the rest is history, right? You end up with, after you do some simplifying, you end up with this equation just like we said you would. Okay? Now, at first glance, that equation, x squared equals 4py, doesn't exactly look like the parabolas that we're used to seeing. It's just written in a slightly different form. But note that when p equals 1/4, let me see if I can make this less blurry. There we go. But note that when p equals 1/4, we get the standard parabola y equals x squared, right? If p is 1/4. All right? The vertex of this parabola is 0, 0. If the vertex were located at some other point hk, and we usually use the variables h and k, then the equation would become y equals x minus h squared plus k. For the sake of consistency, and you'll see this with the rest of the conic sections, we're going to move this constant over so that we've written it in the form y minus k equals x minus h squared. And the reason for that is because then you know that you always change the sign on h and k to tell where the vertex is in the case of a parabola, or where the center is in the case of a hyperbola or ellipse. Okay, as I mentioned on the previous page, in this case the directrix was the horizontal line y equals negative p, but in fact the directrix could be any line, and the ones that we most concern ourselves with are when it's a horizontal line either at negative p or positive p, or when it's a vertical line either at negative p or positive p. So a standard parabola has a vertical or horizontal directrix, in which case its equation is one of the four given in figure 10.4.6 on page 642. So let me show you that at least. 642. Here we go. So it's one of these four cases, right? And so you can see them all laid out there together with their corresponding equations. And so you can see how they all kind of differ, how they compare and contrast. Okay, so that's page 462. Okay. For the purposes of graphing, though, this is the format that we like them in. So if you have y minus k equals a times x minus h squared, this thing is going to have vertex hk. It's going to open up if a is positive and down if a is negative. This thing, x minus h equals a times y minus k squared, also has vertex hk. Notice that h is always the thing with x, right? And k is always the thing with y. And you always change the sign on both of them, okay? At least when they're written in this format, you do. Okay, this thing is going to open right if a is positive and left if a is negative. So none of this should be news to you. Let's just sketch a couple examples. Sketch the parabola and label its focus, vertex, and directrix. So for x squared equals 4y, I'm going to rewrite this so that it looks like one of these two formats. So this would be the same thing as saying y equals 1/4 x squared. And so then I can see that, first of all, a is positive, so this is going to open up. You have a y equals x squared type of thing, so it's going to open up or down. And since this is positive, it's going to open up. And the center here would just be 0, 0. So it's kind of a boring one. Excuse me. So y equals 1/4 x. I mean, so we're going to go, usually we would go over 1 up 1, but we would go over 1 up 1/4 in this case. Over 2 up 4 usually, but 4 divided by 4 is 1, so we'll go over 2 up 1. Over 2 up 1, right? We could go over 4 and up 16. When you divide it by 4, it should be 4. So over 4, 1, 2, 3, 4. Up 4, 1, 2, 3, 4. So you get kind of a, whoops, not that point right there. But anyway, so you get this kind of wide parabola because we're multiplying by a 1/4. But that's how you would do these ones. Ooh, that was not very pretty on the left-hand side. Okay, this one. This one looks like a y squared equals x type of thing, or in other words, it's like an x equals y squared type of thing. If I rearrange this a little bit, I can get it to look like x minus 1 equals negative 1/8 times y plus 2 squared. So the vertex is going to be at 1, negative 2. 1, negative 2. And it's gonna, since it's an x equals y squared, it's gonna open left or right. Since this is negative, it'll open left, so it's gonna open this way. Usually we would go, you know, up and down 1, over 1, to the left 1 in this case. But since we're multiplying by a 1/8, I think what we'll actually do, goodness gracious, we could go 2, and then we'd go up 4 usually, so we'd just go up 1/2. Holy schmoly. This is really wide. This one's really wide. If we went 4, 1, 2, 3, 4, usually it would be 16, but we divide by 8 and get just 2. 1, 2. So 1, 2, 3, 4, 1, 2. So this is a really wide parabola. But anyway, that's good enough to get an idea of what the curvature of this thing is. And that'll do it. That's that. We can also write the equation for a parabola given some information. So for example, let's write the equation of the parabola with vertex 1, 1 and focus 3, 1. So if you think about this, the vertex is 1, 1, the focus is 3, 1. So so the picture that I'm thinking of looks kind of like this. Let me see. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So the vertex is here. The focus is here. Since the focus is at 1, 2, 3, the directrix must be at, oh, hold on a second. I was putting them in the wrong spot. So no, not there. Actually, let me do the correct one in a different color. So we'll go, the vertex is at 1, 1, sorry, and the focus is at 3, 1, 2, 3, 1. I don't know what I was thinking. But anyway, that's the focus, that's the vertex, since the focus is at x equals 3, the directrix would have to be at x equals negative 3. So here's the directrix. And, oh, that's not true. Hold on. Since the distance between the vertex and the focus is 2, the distance between the vertex and the directrix would also be 2. So 1, 2. So it would actually be here. Goodness gracious, how many mistakes am I going to make? I'm going to run out of colors. Okay, so this is the correct one. So there's the directrix, there's the focus, or sorry, there's the vertex, there's the focus. Okay, so it must look something like this. Okay, but at any rate, you'll notice that P equals 2, right? So notice that P equals 2. So I know that this thing has to look like the vertex is at 1, 1, so it would look like this is an x equals y squared thing because the thing opens right. So we would get x minus 1 equals well, it equals a times y minus 1 squared. So you get your vertex at 1, 1. You get it opening right as long as a is positive. How do we find a, though? Well, I know that p is 2. And the format is, you know, x equals 4p y squared. So a has to be 4p. So I know that 4p equals a. I know that p is 2. So 4 times 2 equals a. So a would have to be 8 in this case. So I get x minus 1 equals 8 times y minus 1 squared. Okay. So that's that. Okay. Give me a sec. Okay, sorry about that. Okay, so moving forward. Right, so I feel like I made so many mistakes going through this one. The idea is figure out what P is, use your vertex, right, and also like this graph to know what format the equation is, and then to solve for A, 4P equals A, right? So that's that. Just make sure A has the correct sign, right? In this case, it had to be positive because the parabola was opening right. Okay, moving on. So that's parabolas. Let's talk about ellipses. So an ellipse is the set of points in a plane whose distances from two fixed points in the plane have a constant sum. The fixed points are called foci, plural of focus. I've heard some people call it foci or foci. I have no idea what the correct pronunciation is. I'm going to call it foci. Anyway, so the fixed points are called foci, and the midpoint between the foci is called the center. Again, here's a construction that shows you how to do it. I think they use like rubber bands or string or something and a couple of push pins to create their ellipse. But anyway, when the foci coincide, the resulting curve is a circle. So as I said at the beginning of the lecture, right, circles are just special kinds of ellipses. For ellipses other than circles, the line segment through the foci across the ellipse is called the major axis, and its endpoints on the ellipse are called vertices. The line segment through the center and perpendicular to the major axis is called the minor axis. It is traditional in the study of ellipses to denote the length of the major axis by 2a and the length of the minor axis by 2b and the distance between the foci by 2c. So let me draw a picture. I'm just going to draw you one. Well, maybe I'll draw both kinds. Right? So you could have an ellipse where the major axis is parallel to the x-axis, like this. Right? In which case, so this thing right here would be your major axis. Right, so this is your major axis. And this thing right here would be your minor axis. These would be vertices. This distance from here to the center would be A. This distance from here to the center would be A. This would be B, and this would be B. So the span all the way across would be 2 times A, and the span all the way across here would be 2 times B. Oh, and then the foci, right? So you might have, it's going to get confusing if I try to draw the foci. So, but the idea is that you'll also, that was a very poorly done ellipse, my apologies, but the idea is that you'll have a couple of foci, right? And then the distance from the focus to the center is C, so that the distance between the two foci is 2 times C, all right? Anyway, if the parabola were kind of oriented the other direction, right? So if we were kind of going this way, well, now this would be your major axis, right? And this would be your minor axis, right? So anyway, all right. So the equation of ellipse with foci negative C0 and C0 is x squared over a squared plus y squared over b squared equals 1, where 2a is the fixed sum of the distances between the point on the ellipse and the foci, and b squared equals a squared minus c squared. That's kind of an important point for some of the things we do later on. Okay, so let's prove this fact, right? Let's prove that if you've got an ellipse, this is going to be its equation. So let's say that xy is a point on the ellipse. The distance between f1 and xy would be x minus square root of x minus negative c squared plus y minus 0 squared. Okay? And the distance between f2 and xy would be x minus c square root of x minus c squared plus y minus 0 squared. And since the sum of those distances is 2 times a, it must be the case that the square root of x plus c squared plus y squared plus the square root of x minus c squared plus y squared equals 2a. Well, if that's the case, you can isolate one of the radicals, square both sides, isolate the other radical, square both sides, do some algebra, and end up right here. So I'll let you read through the rest of it, because the rest of this is just, I mean, it's just algebra, right? But this is the case. All right. The foci in the derivation above were on the x-axis. If the foci were on the y-axis, then you would get x squared over b squared plus y squared over a squared equals 1. Also note that in the derivation above, since the foci were at negative c0 and c0, the center of the ellipse was at 0, 0. In general, if the ellipse were centered at hk, then we would get this situation. An ellipse would be something of the form x minus h squared over m squared plus y minus k squared over n squared equals 1. I've changed from a to b. I've changed a to b from, I've changed from a to b to m and n, and I did that on purpose because when we use a and b, a is always we call it the semi-major axis. It's always the half of the length between the two vertices, and B is always half the length between the two sort of minor vertices, where the minor axis intersects with the ellipse. But for the purposes of graphing, it's convenient to just think of like whatever it is that you're dividing the x group by, that's how far you're going to move left and right of center. Whether it's the major axis or the minor axis, it doesn't matter. You're going to have points m units left and right of the center of this ellipse, and you're going to have points on the ellipse n units above and below the center of the ellipse, right? So I like to just use this different convention, okay? Just because it makes it easier to graph. But this ellipse has center hk. Again, h goes with x, k goes with y. Change the sign on both of them. They have vertices m units left and right, and n units above and below the center. Okay, I said this before, so let's just practice. So let's sketch the ellipse, label the foci, vertices, and ends of the minor axis. so the ends of the minor axis, they're not technically called vertices, although I might call them like minor vertices. But okay, let's do this. So this one is centered at 0, 0. So there's the center. From the center, we're going to plot a couple of points, 2 units, right? You take the square root of this number. So square root of 4 is 2. So you're going to go 2 units left and right. And you're going to go square root of 25 is 5, so 5 units. 2, 3, 4, 5 above and below. 2, 3, 4, 5. And then you can connect the dots. And there's your ellipse. Now we were supposed to also label, so we've got the vertices. These would be vertices, right? Right, and this vertex is at 0, 5, obviously. This one's at 0, negative 5. Okay, these are the ends of the minor axis, right? So this one is 2, 0. This one's negative 2, 0. But then we were also supposed to label the foci. Okay, well, how do we do that? Well, that's where this little fact comes into play. Remember that c is the distance from the center to the focus. And we know that b squared equals a squared minus c squared. We can identify a and b really easily. Right? A in this case is 5, and B in this case is 4. So again, C squared is what? B squared is A squared minus C squared. So we could rearrange this and say, so C squared is A squared plus B squared, right? So it's just Pythagorean. No, that's not right. C squared. Negative c squared would be b squared minus a squared. So c squared is a squared minus b squared. So my apologies, it should be minus. C squared is a squared minus b squared. Okay, so here we go. So c squared should be a squared minus b squared, right? So c squared is 21. That means c is the square root of 21. Square root of 21 is approximately 4.58. Okay, and then remember that the foci are along the major axis. So in this case, that would be the y-axis. So we go 1, 2, 3, 4.58 or whatever. So there's one focus, and then there's another one. All right, so that's a focus, and it's at 0, root 21, and that's another focus, and it's at 0, negative root 21. Okay, so that's that. Let's do another one. This one, okay, well, we've got to fix it up first. Let's divide by 16 so that we have a 1 on the right hand side. We would get x minus 3 squared over 16 plus y plus 2 squared over 1 equals 1. Okay, so center's at 3, negative 2. 1, 2, 3, negative 2. From the center, we're going to go 4 units left and right. 1, 2, 3, 4. 1, 2, 3, 4. And 1 unit up and down. Ugh. I don't like these. I don't like these really thin ones. I don't know. They're not. I didn't do too bad. It's just hard to get them to look nice. But there you go. So again, we have vertex here. I'm not going to put the coordinates on it. What about the focus though, or the foci? Well, again, it's going to be c squared equals. Notice that in this case, a is 4, so a squared is 16. So it's a squared minus b squared. Right? So a is always the larger of the two numbers. So c squared would be 15. So that means c is the square root of 15. That's about 3.87. 3.87. They're along, so c, now that's the distance from the center to the focus, and it's always along the major axis. In this case, the major axis is this guy right here, right? So we're going to go from the center, 1, 2, 3.87, so almost all the way to 4. Focus. The foci are not always as close to the vertex as these last two examples. Okay? It's just because they're skinny that this is happening. Both of these examples had like kind of skinny ones. If you had more rounded ones, then the foci would be closer together and therefore further away from the vertices. Anyway, here's another example. It says, find an equation for the ellipse with foci at negative 1, 0, and positive 1, 0, and b equals the square root of 2. By the way, you could be given all kinds of information. You could be given all kinds of information about these things, and you just have to use your problem-solving skills to try to figure out what ellipse they're talking about. In this case, let's see if we can get our bearings a little just by drawing a quick sketch. So the foci are at negative 1, 0, and positive 1, 0. Okay. So the ellipse, now I don't know if it's like wider than it is tall, but I know that it goes around those 2 points. Now I also know that the distance between a focus and well, hold on a second. Now I do know that this, okay, because the foci are always along the major axis. So I know that this does actually have to be wider than it is tall. So I do know a little bit about this. It's got to look something like that, right? But I know that this distance right here, from the focus to the center, this distance has to be 1. This distance has to be 1, right? So c equals 1, in other words, right? Okay, so c equals 1. And we're given that b equals the square root of 2. So we can find a pretty easily, right? We can say, a squared would have to be b squared plus c squared, right? A squared equals b squared plus c squared. So a squared equals b squared plus c squared. Whoops. So a would be the square root of 3. Okay, so since we have a and b, and since we know that that the major axis is along the x-axis, and since we know the center is 0, 0, okay, so we know that this thing would have to be x over a. Actually, it's x over a squared, isn't it? Plus y over b squared equals 1. And that's that, right? So this would be, and it's x squared, right? Okay, so this would be x squared over 3 plus y squared over 2 equals 1. There's the equation for that ellipse. Okay? Again, we put the square root of 3 under the x squared because we knew that the major axis has to be along the x-axis, since that's where the foci are, right? The foci are always along the major axis. All right, so that's that one. That's how ellipses work. Let's talk about hyperbolas. So a hyperbola is the set of points in a plane whose distances from two fixed points in the plane have a common difference. The two fixed points are called foci. The midpoint between the foci is called the center. I don't know why I just said is center, but it's called the center. And the line through the foci is called the focal axis, and the line through the center and perpendicular to the focal axis is called the conjugate axis. So these are sort of similar to major and minor axis, except that a hyperbola doesn't always open up along its major axis, but it does always open up along its focal axis, right? Anyway, the hyperbola intersects the focal axis at 2 points called the vertices. Again, you can look at a construction of this if you want. I'm going to skip this proof, okay? Most of it is actually written out for you, but all you have to do is find the distances between the point and the focus, and then the absolute value of the differences has to be 2a. So you would have to do this absolute value of this minus this equals 2a, and then that leads to all the rest of it. So that's that. Give me a second. Okay. Man, I get interrupted so many times these days. It's like everyone's just so used to working from home and whatever that like nobody cares anymore about trying to be quiet. Okay. Anyway. So just as before, right? This is just one kind of hyperbola. You could have a hyperbola with foci at C0 and negative C0 instead, right? Or whatever. So in this case, so in the derivation above, the foci are on the y-axis, and in that case, the hyperbola opens up and down. If the foci are on the x-axis, then the hyperbola opens left and right, and we would have a different equation, right? Also note that the center of the hyperbola was 0, 0, but in fact the center could be anywhere. One thing that I do want to look at with you real quick is that be careful when you draw hyperbolas, because the tendency among students a lot of times is to just draw them as two parabolas, but that's not what a hyperbola is. They're very different. So I wanted to just show you, right? This is a hyperbola, and as you zoom out, you'll notice that these look more and more like straight lines. It just looks like an X. In fact, these are the asymptotes that the thing approaches. So they never curve away from their asymptotes. The more you zoom out, the closer they get to their asymptotes. So when you're drawing this curve, you should never draw the curve so that it eventually veers away from its asymptote, right? And just to show you that, right, here's a parabola, right? So a hyperbola is not just a wide parabola, because notice that the parabola down here starts out wider than the hyperbola does, but eventually it gets more steep and it veers away from those asymptotes, which is not the kind of behavior that a hyperbola exhibits. So the point is, a hyperbola is not just a wide parabola. It's not just two parabolas stacked on top of each other or next to each other. It's got a different shape, right? And as we saw, it approaches these asymptotes. So most of the work for graphing a parabola involves finding what those asymptotes are. Okay. So, but here's how we'll do it, okay? So, hyperbolas are going to have one of these two forms. Either the x group will come first or the y group will come first. If the x group comes first, then this thing opens left and right. If the y group comes first, then this thing opens up and down. In either case, though, the center is hk, where h is the thing with x and k is the thing with y. This one will have vertices at plus and minus m. This one will have vertices at plus or minus n. Okay? And the asymptotes in both cases are plus or minus n over m times x. Y equals plus or minus n over m times x. Now again, this is just using the formulation where m is always the thing you're dividing x by and n is always the thing you're dividing y by. So don't get that confused with a and b. A, in the canonical sense, a is always the focal axis. Or rather, it's the distance. A is always the distance from the center of the hyperbola to a vertex, right? And B is always the distance along the conjugate axis. In other words, it's the distance from the center to, well, nothing on the hyperbola, I suppose. But it's just sort of the length of that focal or of that conjugate axis. Anyway, so you could memorize that, right? You could memorize that, oh, I know that the asymptotes are going to be y equals plus or minus n over m times x. But to avoid having to memorize it, what we'll do is this. We're going to plot the points m units left and right of center and n units above and below center. And then we'll use those points to draw a box. And then we'll draw the diagonals of the box. And those are the asymptotes. So let me give you a couple examples. So y squared over 9 minus x squared over 25 equals 1. Okay. Remember, a is always the thing you're dividing x by. So a is 5, and b would be, or sorry, that's not true what I just said. M is always the thing you're dividing x by, and n is always the thing you're dividing y by. So m is 5, n is 3. The center here is 0, 0. So here's the center, where we're going to go 5 units left and right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3 units up and down. 1, 2, 3. 1, 2, 3. And then we draw a box. Like that. Okay, and then we draw the diagonals of the box. And those are the asymptotes, right? Now, because the y group comes first, this hyperbola opens up and down. So that's actually a vertex, and that's actually a vertex. And so the curve ends up looking like this. This is kind of a wide one. But remember, you never get further away from the asymptote. You should always get closer and closer to the asymptote as you move away. All right? So there's that hyperbola. So we've got the vertices, the asymptotes. We didn't get the foci on there. So what about the foci? Well, the distance between the center and the focus is going to be c, and the relationship between a, b, and c is given to us right here. So b squared equals c squared minus a squared. All right, so c squared is going to be b squared plus a squared, right? So c squared is b squared plus a squared. Let's make sure we get this right. So a is the focal axis. In that case, that would be the y-axis. So a would be 3 in this case. A squared would be 9. So, and b squared would be 25. So c squared is 25 plus 9. So c squared is 34. So c is the square root of 34. Square root of 34 is approximately 5.8. So from the center, I'm going to go along the focal axis. I'm going to go up 5.8. 1, 2, 3, 4, 5.8. So there's a focus. And 1, 2, 3, 4, 5.8. So there's a focus, right? Okay. So that's what that hyperbola looks like. Let's do part B. So center this time looks like it's going to be at 1, negative 2, 1, negative 2. I feel like we just did something like this. But anyway, we're going to go 2 units left and right. 6 units up and down. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, another wide one, right? Anyway. Okay. And this one's going to look kind of like that. Okay. So that's that guy. As far as the focus is concerned here, c squared again is b squared plus a squared. But this time, the focal axis is going to be the thing we're dividing x by. So it's going to be 4, right? So c squared would be, so a squared is 4, b squared would be 36. 36 plus 4, c squared is 40. So c is the square root of 40. Square root of 40 is about 6.3. So from the center, I'm going to go along the focal axis, 1, 2, 3, 4, 5, 6.3. And 1, 2, 3, 4, 5, 6.3. So those are the foci. Okay. So there's your hyperbola. Again, the only difference between the only reason this is opening left and right is because x comes first. If you switch the order of subtraction here, it would be opening up and down. So it's not because it's wide. You don't always sketch the wide part. You just sketch the part that comes first. Okay. Okay, and then number 6 says, find an equation for the hyperbola with foci 0 plus minus 5 and asymptotes y equals plus or minus 2x. Ooh, that's kind of interesting. Okay. Well, goodness gracious. I mean, I know that y equals plus or minus n over mx. So n over m has to be 2. What other pieces of information do I know? I know that the focus, or the foci, are plus or minus 5. So c equals 5, right? So I know that c equals 5. But I also know, since the foci are along the vertical axis, I know that I've got a situation like this where this opens up and down. Not like this where it opens left and right, because then the foci would be like, they would have to be plus or minus 5, 0, right? Opens up and down. Okay. I think here I need to say a little bit more than just n and n. I need specifically to know what A and B are. Since I know that this opens up and down, the focal axis is along the y-axis. I know that, well, I know that the major, or the focal axis is the thing that I'm going to be dividing y by. What I'm struggling with is I'm not sure how to tell that from just n and m. Well, shoot. Well, maybe it doesn't matter. I mean, we know that c squared equals a squared plus b squared. We also know that n or m is a. We're just not sure. We're just not sure which. Is there a way to tell? Well, n equals 2m. Yeah, it doesn't really matter. It doesn't matter. If I call A n and B m, I'm going to be putting n squared and 2m squared. If I do it the other way around, I'm going to be putting 2m squared and n squared. So it doesn't matter. It doesn't matter. In fact, I can replace these with n and m, and it wouldn't make a difference. Okay. Oh, good. That's good. So then I can say c squared equals n squared, or sorry, n is 2m. So I'm going to say c squared equals 2m squared plus m squared. So c squared equals 4m squared plus m squared is 5m squared. C squared is, c is 5, so c squared is 25 equals 5m squared. That means m squared is 5, so m is the square root of 5, and n would be 2 times the square root of 5. So what do we get? Okay. So m is always the thing that we divide our x group by. Okay, and moreover, the center is at 0, 0. So this is going to be x squared over m squared. Oh, but it opens up and down, so y has to come first. It's going to be y squared over n squared minus x squared over m squared equals 1. Okay, and there's our equation, right? So we would get y squared over 4 times 5 is 20 minus x squared over 5 equals 1. There's the equation for our hyperbola. Okay, has to be. See, the a and b thing was messing me up. N and m I think is better because n is always what you're dividing y by, m is always what you're dividing x by, and you can tell which way it opens just by looking at the foci. Okay, so you don't need this a and b nonsense, where a always has to be the focal axis and b always has to be the conjugate axis. It's just kind of silly. Anyway, that's that. So that's your brief review of conic sections.